maybe the coolest thing to happen to computer science since, well, I would say lazy evaluation, neural networks, and quantum are like the coolest things happening in computer science right now, right? And I'll explain why. Okay, so what happens when you have a gigantic data set, right? So I'm going to sort of dissect what happened yesterday when we dealt with DAS. Okay, so we had a data file, okay, or a file. It's the data source I'm showing, right? So let's say this is our data, right? And we discerned that it was, for whatever, it was big. Right? We had a big data problem. Okay? So what we did is we said we can't deal with this as is, right? Traditional, we can't vertically scale for this. We've got to go out horizontally to deal with it. Okay? So what that means is, and this is typical computer science, right? Really logic solutions. We break the problem down. Right? So we took this big data set, right? And we said, let's take it and split it into smaller pieces, right? So this becomes, let's say, data, sub-0, okay? And let's do shift here. And then you'll have another set over here, which is, say, data sub, we'll just say n, right? So we break it up into a bunch of smaller sets, okay? And then what happens is, we're out here, okay? I like the diamond eyes, actually, so let's do this here, here, and here. Okay, so great. So we're out here, and we're interfacing with this data, right? But behind the scenes, what's happening is, yeah, that's good. Behind the scenes, it's being cut up for us, right? Then we are not really aware of this, okay? But behind the scenes, the data is being split up for us. Okay, that's great. But the other thing that's happening, and this is like the key point of this, what makes this go, all right, is there is an enormous amount of parallel algorithms at play. All right? Anybody have experience with parallel algorithms? We do it all the time, right? As you sit here in this class, you are listening and participating and breathing. The blood is flowing through your body, right? There's all kinds of stuff happening in parallel right now, right? And that's what makes us more efficient. So it turns out in computer science and in data science and really in all fields, there's always room to do things faster, right? And there's generally always a way to find a way to improve by doing things in parallel, right? So multitasking, okay? So what makes this go, right, is there are, we call them job schedulers, but let's just say managers, good managers, okay? There are managers at play saying, okay, you want to run this algorithm, right? Or you want to run these steps, okay? So they take that as an input, right? So let's just say they take these algorithms and steps as an input, right? And what they do is they come up with, this is like the big breakthrough, right? This is what makes it go, okay? They come up with the most expedient plans, sorry, let's just say fastest execution plans. It's about planning, okay? So some of you may have already seen this. So does anybody have experience writing like SQL queries? So if you haven't, that's okay. So what happens is when you run a SQL query, okay, you say, select, you'll say something like, okay, select star I'm going to say vaccine, okay, where safety is greater than or equal to 99 point, change that, 99.99%, let's say, okay? Well, there's no percent here because that would be wrong. Let's just say this, okay? So this is an example of a SQL query. Now what happens is you've got a table, right? You've got a table which houses this data, right? And you're saying, give me all the columns, right, from this vaccine table, where the safety, and so there'll be all these fields in it, okay? So one of them is safety. Let's say the other one is, I don't know, brand, okay? Or safety is greater than such stuff. So it turns out that there are things called query optimizers, okay? And what they do is they look at this query and they say, oh, okay, he wants all these fields, right? And he wants it from this table. So let's go allocate, resources towards this, right? And let's see if we can improve the memory management we have towards this, right? And, maybe build an index on the fly for the safety column, right? So they do this optimization. And they can do that because they have an understanding of what the table structure is, right? So you execute this, it never just goes straight into this database, right? There's a step of optimization that happens, right, that says, okay, let's find the fastest way to get you back this result, okay? So the same thing, right, happens when you deal with distributed systems and big data, right? The same thing happens. So now when you go to run these algorithms or these operations, like yesterday we did a bunch of joins, we did some shows, we then ran a machine learning algorithm on it, right? When you do that, the same type of optimization is occurring, right? And that ability to run in parallel, right, is what allows this to work. And so even when you go, and let's say we fast forward, I always talk about quantum, all right? So when we talk about quantum computing, right, and that is unequivocally the next, gigantic leap for computing for us, right? So the concept there is if you have more than 2 to the 70 qubits, right, this is if somebody calculates 2 to the 70 for me, that'll be fantastic. Please don't melt Google trying to do it, okay? But it's big. Big number, all right? So if you have more than this, okay, then you can store the whole, world data, okay? That's the big thing going on here, all right? So we talk about quantum is faster. It's going to change things. We'll decode the genome in seconds. We'll figure out everything there is to know about a situation in seconds, right? It's not because there's some type of speed limit that we've broken. That's not it. It is because this amount of memory, right, allows you to keep track of things we could not before. So I think we were talking yesterday, right? Kenneth had created a system that had the whole world's data in it, okay? And the aliens have decided that they want access to this system, okay? And so now the galaxy is coming in and saying, please give us this amazing data that Kenneth has, right? So it's your fault, Kenneth, right? They're coming, okay? So they've decided they want it. Okay, so Kenneth says, no problem, all right? In order to pull that off, right, to satisfy the velocity, right, the aliens are going to wait no more than, let's say, 3 seconds, right? So in order to get everybody, all these aliens across the galaxy, the data back in less than 3 seconds, I need, let's say, 1 billion servers. Okay, I need a lot of hardware to make this happen, right? So okay, so he submits it to Howard, okay, and the university says, okay, fine, you can have 1 billion servers, okay. But those of us who have been in like leadership positions and management positions, I know, I sympathize with you, okay. It becomes a nightmare to manage that many resources, right? You could argue that a lot of our inefficiency is because it's difficult to manage what's happening, right? And so how do you manage communication between 100 people and a single manager? Somebody's going to fall within the cracks, right? It's a problem. And so the same phenomena exists in computer science. Same issue, right? So this worker, so now let's say the university says, okay, go for it, right? You get funding. They bought you 1 billion servers. Congratulations, right? And you had to, in order to put those 1 billion servers there, you built a shield around the earth made of servers. Something incredible, right? But you've done it. So now there has to be some bosses of these servers, okay? And even if you take the approach of, let's say I don't like saying, I'm going to call them bosses, right? So let's say you have a boss over here, right? And that boss has, let's say you're trying to be practical, you realize that one boss can't manage 1 billion, right? So let's say you give each boss 1,000, right? So one boss is going to get, say, 1,000 servers, okay? Well, you still have, this is what, you still need 1,000 bosses, right? I believe that's correct. 100, yes. So I think it's more than that, right? So you would need 100,000 more bosses. Okay. So in order to manage all of them, right? Because you've got 1 billion. Okay. So now, now what happens is, even if you have that, so you have boss and boss and boss, and there's an ultimate boss, right? And all this stuff is going on, okay? And they're all reporting back because they have to stay in sync, right? The memory requirements involved to pull off this kind of synchronization, right, are astronomical, right? Somewhere probably approaching 2 to the 70th, right? And because what happens is whenever you say, okay, let's say this boss says, go do operation, let's say operations, right? He's going to execute, these things need to happen, right? So he's going to give us a list, right? And there'll be, some operations from here to end, right? Whenever that happens, there has to be a record that these operations have been requested, okay? And so as you do that, then the worker gets it, this worker gets it, okay? And we go on and on, okay? So that has to be tracked somewhere. And if you have thousands, billions, and thousands of operations coming through, very quickly, and I can't believe it reduces to this, but the bookkeeping, right, of the operations will explode. You will have a big data system that has big data problems of its own because of all of the management involved to get the job done. Everybody with me? Right? It's complicated, right? We can feel it because of management. We already know it's not that efficient, right? So, and that's why you can see small organizations running past larger organizations because even though they have less people, they're able to execute, right? They don't get lost in these cracks, right? So now we realize that we need an enormous amount of memory to make it possible for galactic operations, okay? And so that kind of memory only comes from processing at the quantum scale, right? It only comes from memory at that size, okay? And so that is why quantum is faster, right? Quantum gives us the ability to have tenants run 1 billion servers without them running out of memory. That's what's going on, right? It's not that it's, the electrons are juiced up, right? It's not that. It's that they have found a way to store an enormous, an exponential amount more of information at a small size, right? And that allows us to have that much more memory, and that much more memory allows us to do that much more in parallel. Everybody with me? Kind of with me? Yes. Good. So that is why these big data techniques are so important, right? And, learning that memory is a big problem, we have a way to deal with that. At some point, the amount of servers, like we're talking about 2. Kenneth's example is 1 billion. At some point, that will become a reality, right? And I'll show you again today how amazing this parallel execution is. And not only that, how clever the machines have become at executing things for us in parallel. The optimizations they're making are now no longer at like the SQL level. They are figuring out the best way to traverse through like any data set, no matter where it is. If it's in memory, they can cut through it, right? So, okay, so it all kind of ties together, right? The takeaway for this is big data, okay, and ML, let's say this, machine learning, right? The combination of these two, right, are able to work because, right, of parallel execution. This is what it's about, right? How good are you at managing things in parallel? That is what makes this go, right? Okay, and quantum, same thing. And we learned that this parallel execution, right, is dependent on the ability to store operations, right? And your ability to work in parallel instead of doing something like this, right? Instead of doing something like that, let's do one more because it's more fun to draw graphs this way. The idea is you want to be able to do, this is just an example of this, right? Right? Break it up into parallel as much as you can, and we'll get done faster. Okay, okay, good. Now, with that being said, let's walk through a practical example of this. Does anybody have any questions?
Yeah, Prem.
Okay.
So
yeah.
this assumes that the job is embarrassingly parallel, right? So if it's something that you depend, let's say I depend on Nana for something, then I'm going to have to wait till Nana is done, and then you can look at it as being scaled up. So if you have something that depends on something, then breaking it into parallel becomes a challenge. So how does the like that do that? I mean, this may be if it's out of context, we can go and then we'll explain it later on. But
yeah.
Right.
No, this is an excellent point, right? So some things cannot be broken into parallel, right? There are some things where you have to, and that's, an example of that is, and here's how we deal with that, okay? So first I'll show you an example of how we deal with the dependencies, right? They're called fork and joins in computer science lingo, right? And then I'll show you an example of how the problem is solved in general, okay? And why, and I'm telling you this parallel execution thing, our speed is very important. If you're able to execute in parallel faster than another advertiser, you will win the money. If you can figure out how to execute in parallel to decode how to defeat this virus, you will defeat the virus, right? So, you know, these viruses in biology already work in parallel. You know, they are working as fast as possible, right? So we have to get there. Okay, now, this is an excellent point by William, right? So let's suppose that you have a dependency, right? So you cannot do, and this is an example over here. So we have A, B, C, and let's say this is end. I'm going to just draw this as end, okay? So we have to do A, B. So this is how it's going right now, okay? And what we want to do is break it into parallel, all right? And let's suppose that, and we can know this, right? So the optimization algorithms and managers are able to see from looking at code whether or not you have a dependency, right? They can trace this, right? And so what they'll say is, and you'll see it today, like it basically means that a function depends on another function, right? So when you have this nesting, then we know that they're, you know, related to each other, right? One has to happen before the other. But if there's no nesting, and that shows up in the call stack, right? If there's no nesting between us, then you can go, okay? And so, and again, this comes down to this bookkeeping, right? So what happens is we have this thing called the call stack, right? Call stack. And what this means is this is like, okay, so there's a function over here, right? And there's a function over here, and we have all these, you know, functions that have to execute, okay? And we can find out that, you know, this function was maybe called by this function, right? And so if you see this dependency, right, we know that it has to execute in series, okay? But if you have a function here, like f, let's say this is f0 and this is fj, okay? And fj and f0 have no intersections in the call stack, fj goes, right? This is like the technical of it, right? So we can parse this and then we see it. Okay, now, and so what happens in this situation, if it turns out that we have, this is A and B, and then we have, let's say, C over here, okay, then what happens here is you'll have to do, A has to go into B, right? So you have A. So this is William. William has to talk to Nana. I would argue that everybody has to talk to Nana at some point, okay? And I'll show you a graph of, we'll call it the Nana graph, okay? Nana, are you in the audience? Yeah. Yeah, I
Yeah,
see you.
I'm right here.
Okay, good. Yeah. So then we have A and B, right? And we have end over here, right? But we know that C can run, okay? So what will happen is, and it, so what will happen is that there'll be a join here, right? So A and B will run, and then there'll be a point over here where we join and we come to end. Or you can have it just run like this, right? So C will finish, execute, and then A and B will execute. Now, let me show you what happens when you have a non-dependency, okay? And this is the most common pattern we see with parallel algorithms, right? So, and I'll give you an example, right? So let's say that you have a website, okay? So this is some site, right? And you want to find out the performance of this website. This is very important because if you don't go at, let's say you, for example, let's say you have done some research and you want to publish your research on your own website because you think it's very valuable and, you know, you want to get it out to the world right away, okay? So, you know, you get a server, you stand it up, you put up the website, and you're like, okay, it's great, it's there. But what you may not know is how many visitors your website can handle before it starts to struggle, right? And so the only way to know that is, like with all things, you have to perform QA on it, right? And so you've got to simulate the situation, right? And so there are tools to do that, load runners. I happen to like this thing called Selenium. And so what basically happens is we dispatch a whole bunch of users through software, okay, to come in here and hit the website and get back the value that you expect. right? And then and we track their times. So this guy's going to take, time 0, he's going to take time 1 down to time n, okay? We track their times, right? And then we will take some statistics on their times, the worst, the best, the average, confidence intervals, etc., okay? And we'll create a report, right? So very common use case. You want to know, is it a website? Is it a product you've created? Is it a theory you've come up with? What happens when, a bunch of things are happening at the same time, right? How does it scale, okay? So the way that looks programmatically is you have a start, okay? And what we're going to do is we're going to come out, and then we're going to fork, okay? And this fork literally is a fork. Well, that's a computer science fork, okay? Fork, okay? And this goes on, right? And each one of these is going to be one of the workers you've created. Worker 1, all right, to worker n, okay? And they're going to go off into the world and try to figure out what this website's doing, right? So they're all going to go execute, 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 okay? And you want them all to finish, okay? In order for this process to finish, Nana has to check it, like with all things, okay? And so we have a Nana process over here. Nana, I'll capitalize your name, I apologize, okay? So over here, waiting for us is Nana, all right? And what happens here, and Nana, in computer science terms, is referenced as the join, okay? So we all are running, and then what will happen is we will run into this point, okay? And everybody's going to wait until Nana can come through and tabulate the result, okay? And this is the join layer, okay? So we up here, we split. Everybody's going out and doing their thing, and then we're going to wait. Maybe this guy finishes first, second, third. Maybe it happens in order, okay? But nobody gets past Nana until everybody's done, right? And then Nana is going to do some computations, and he's going to call me late at night and tell me to do something, and I'm going to have to do it, okay? And then we're going to go on, and we're going to get to end, okay? So, sorry, let's do end here. Okay. I drew it as a stop sign. That's great. So that's an example of a very common pattern. I would say this happens probably every day for Nana. We also refer to this as single points of failure. Okay, but it's a common attack, right? We break people up, and so you can imagine these are like all the lecturers. Okay, and we're all submitting stuff, we're doing stuff, and nothing gets published until Nana explains us how to do this and puts it together for us and whatnot, right? So, okay, so an example of dependencies with joining back in, right? And nothing is to say that this is the only join point. You could have had an internal join point over here, right? We broke everybody up, and then maybe worker 1 and worker 0 and worker 1 have to sync, right, before they go forward. And everybody still has to sync at this point, right? But this is the idea. It's just divide and conquer and go. And so very, very common, very, very useful. And a lot of this is, so okay, here we go. So where do you set the join points, right? What if you don't have, how can we set it intelligently, right? And it turns out that from examining the call stack, right, and examining the interpreter can look at the code, it can very intelligently figure out how to build this parallel execution for us, right? And so, and this is what's going on. This is what's going on to make these things work, right? In fact, when you look at a data lake, which is just a file system in the sky, Dropbox, okay? It looks like one big server to you. It looks like one location, okay? But it's not, because we know that it is impossible for something that big to exist. It's a facade, right? What is really happening is there's a bunch of bosses back here, okay, that are talking to a bunch of workers back here, all right, that are on their own little servers, okay, that make this look like one big data lake. Or if I write in cursive, it doesn't confuse it as much, okay? One big data lake. It appears like it's one entity in the sky, but what's happening is the parallel algorithms that are running between these servers back here are making it look that way. And it looks seamless, but I assure you, there are multiple servers at play, right? And the management of this, like you don't, if you write over here, you're actually writing maybe over here, right? But you see it as one thing, you see? So it's very, very smart execution of parallel algorithms that are making most things work at scale now, okay? All right, good. So any other questions on this? Okay, let's get into an example.
Excuse me, I have a question.
Sure.
You had mentioned that, so if there's no dependency, then it goes, in this situation here, if you can't find a dependency or join, where does it go? I mean, it just does not compute, or how does that?
Excellent question. So, yeah, This is an excellent question. So, so let's say we're up here, right? And you have all these workers, okay? And let's say we built the Nana bridge, okay? But there is a workaround to the Nana bridge. That happens to be John, okay? So John has the tickets to bypass Nana, okay? I think, at least I think so, Nana, sorry, okay? So what happens is if John doesn't have any dependencies, he doesn't have to wait, right? So there is, let's create the John process out here, right? There's John out here, okay? He is able, since he doesn't have any dependencies, I'm going to draw him in a different color. John can bypass all of this and go straight to the end. And that would be like bypassing the publishing process. He doesn't have to wait for Nana to check things. He can go straight through and say, this is what, is going to be in module 6, right? So if there's no dependencies, you execute straight through without having to, and this key point, without ever having to see any of these join operations. Does that make sense?
Yes, it does. Thank you.
Yeah, that's good. And so we are trying our best in the field to avoid doing all this, right? So this comes back to, yesterday when we were talking about, before you had ETL, right? ETL, and you had all the sources, okay? And so they come to ETL, and ETL puts that into some type of data warehouse, okay? And then all of us users, right, have to wait for the exalted schema. I'll just scratch this out. Data warehouse, okay? We have to wait for the exalted schema to come out before we get the data, okay? This is the old way of doing it. And so it's the same thing is happening, right? Like this ETL has got to figure out, well, do I need you? Can I do source one without you, right? And so this is a situation where we have to plan accordingly, and we have this complexity, right? And so we try to get away from that and act like John, all right? So in our situation, we have now source 0, source 1, and let's say John is out here, okay? And instead of going to the data warehouse, we go to a lake or a file system or some point we can all get to, right? So we have effectively eliminated Nana, right? And so everybody is writing in here, right? They get their own little playground, right? But there's this routing has been eliminated, right? The intelligence of who's doing what and the synchronization, sorry, Nana, but we've eliminated him in the publishing of this, right? And so, and then on the other side of it, we're all coming directly for this data and putting it together ourselves, right? So the automation, there's two ways to do this. You either eliminate this or you efficiently automate it. Because this is the bottleneck, right? This is the pain that's going on, right? I can't get the data. Maybe there's errors, maybe there's communication issues, but more often than not, it is because it's tied up in some process ahead of upstream. It's not ready yet. You need to wait 2-3 months or a couple of days or whatever it is, right? So, your question is very important because the rogue or very efficient processes are how we're trying to execute in the enterprise today, right? Eliminate the bottleneck or make them as efficient as possible. Sometimes you can't do it. Sometimes you can't get around it, right? So if that's the case, you make it as efficient as possible. Good question. Anybody else here? Okay. So let's share a different screen. I always get the windows mixed up. Okay, so let's move this out here. Oh, and it's on the screen now. That's right. Okay, so I'll stop sharing here. And I'm going to share. Let's share this screen. Okay. All right, and I will give you an example of this actually happening now, right? So, write this over here. Oh. Okay, good. And we need, okay. All right, so this is the notebook we saw yesterday, all right? And I'm just going to walk you through the parallel execution point so you can see it, right? And then we'll talk about Spark, and then we'll talk about some internals. Okay, so I'm going to launch this. This is the UI, which has the executions on it, right? I'm glad that it is somewhat minimized. Didn't want to do that. Okay, let's put this over here. Okay, and now I need to come back to the other Jupyter window, which I think is here. Okay, and I'll drag this over a little bit so we can see this better. And I'm just going to go to tasks, actually. All right, so for threads, okay, so we have 2 workers, and they have 4 cores, right? And so what this basically amounts to is this is one execution possibility, one execution possibility, one execution possibility. So each of these are graphs in time of processes that can run in parallel, right? So I'll show you that, right? So let's do, let me pull this over a little bit so you can see it a little better. All right, so what we're going to do is we've created the client, right? So we're going to read in the data, okay? So nothing happens here because we didn't call a compute, right? And oh, so here we did, yeah, because we read the CSV, that's right. Okay, so what happens is if you remember when we were just talking and I was drawing this, the efficiency of how the algorithms are run in parallel is the key step. Can we keep track of it all? And so do we have enough memory to manage it as we go to 1 billion servers? And can we intelligently figure out what can be done in parallel without having the programmers figure it out? Because we will mess it up. There's too many things going on, right? So what happened here, let's see if I can pull this over more so you can see that, right, is it decided, and this is a single worker right now, which is why it's used all of this, and it's also minimized, but you'll see when we break out into parallel, it'll come out in different shades. It read the CSV, right? And then we did a head operation, right? So yeah, because I did data.head over here. I didn't see because it was masked in this display. So, and that happened because we did this data.head, because we actually requested some data. It went ahead and pulled it, right? But if I do this, right? Let's run this again. Nothing happens, right? And that is what you want, okay? Because if you force the action to occur, then it's going to do it as you asked for it, right? But maybe you don't want to do everything as you asked for it. Maybe you want to say, I need all of these things, and computer, find me the fastest way to get that. Break it for me in parallel. Because if you ask for it in order, you're no longer in parallel, right? I want the data that's in the first frame, and I ask for it. Bang, okay, here's the data that's the first frame. But what if I could have read the first frame and the second frame, or the first data source and the second data source at the same time, right? That would save us time, right? We don't have to wait. And so let's see if we can do that, right? So there's an operation here. Notice that we usually, when in Python or in Jupyter, when you leave the data frame as the last entry, you see the results of the frame, right? Here we don't see that. Because again, this is this lazy evaluation, right? Lazy evaluation is, it's not going to happen until you, as the user, say it must go, right? And that is effectively Nana calling us saying, okay, everybody needs to get started now, right? Like 4 days ahead of lecture, you'll get a call from Nana, right, saying, all right, we need to get organized, right? And that is effectively what happens here. Once that call comes through, once we say, all right, show us the data, right, all of us, the lecturers, the administrators, QA, we're all going to come together and we're going to try as efficiently as possible to get this done, right? That's the same thing that's happening in code now, right? So let's look at that, right? So here, we did not actually do the data. We did not actually do this yet because we haven't got the Nana call, right? We haven't got the call to actually execute it. So this is all being added to a call stack for a possible optimization, right? So we'll see that. Okay, so now there's a call to get reading the fundamentals of Tesla, right? And we call head, right? And so if we do this, you should see, right, there's the call to read the CSV, there's the call for head. Notice that this happened down here on a different set of workers, and this happened up here, right? And also notice that this had to happen afterwards. There's a dependency here, right? There's no way you can do a head call on a data frame without reading it. Everybody with me? Yeah, good. So, but what happens if we, let's see if we don't do this here, okay? All right, and I'm going to just kind of execute this again, right? So I'm adding this. All right, we're just executing again, nothing's happening, all right? And we're going to tell the computer that we want to read the frame, but not actually execute it, all right? And we're going to tell the computer that we want to do this conversion, all right, but not actually execute it. See, there's no data here, right? It's all getting added to this optimization group, okay? And so now we don't have to do it here either, okay? And in practice, when you're doing this stuff, you'll execute heads and whatnot because you want to look at the data to make sure you have it right, okay? But in practice, you'll remove this so that the compiler and DAS or Spark, right, can come in here and say, this is the fastest way to do it. It will optimize the execution for you, right? So let's see what happens now. Okay, so if we run this, I did something. Let me jump out here. Good, right? So let's do it again. I think it was lost in the graph. So I'm going to do this one more time. Okay, yeah, so let's see if I can zoom in here. Wheel zoom. And then we're going to scroll to the right. Okay, so look at this. All right, this is an example now of parallel execution. Okay, there's a read CSV up here. And at the same time, there's a read CSV going on over here. A little bit ahead, right? But they're happening at the same time. You see that? So right there, without us doing anything, okay, DAS figured out that it could read in those files in parallel, right? And imagine those files took an hour each to read in, right? So if you did it in series, it takes you 2 hours. But if you do it in parallel, maybe it's an hour to an hour and 15 minutes, right? So here is an example of how, they are able to see this, right? There's no dependencies in the call stack. It will run it in parallel for you. And this is colossal because, so it's like video game programmers, right? They have three big skills. Video game programmers have 3 big skills. 1, very good at math, right? They're running simulations, okay? 2, excellent at running and writing code in parallel, right? It's got to be fluid. There cannot be bottlenecks. You can't be running and things just get stuck. It's got to be smooth, right? Only way you get that smoothness is a whole lot of stuff is being running in the background for you, right? And 3, they function very well without sleep, okay? So it's a talent, okay? Like not everybody can do that. So, but for the rest of us mortals, okay, who need sleep, who are okay at math, okay, and aren't, have separate compilers in our minds to build this stuff, right? We can use these execution engines to find the efficiency point, right? And this is important because we're racing. We're racing against the virus, right? We're racing against publishing. We're racing against other companies, right? So efficiency is, what is it, next to godliness? I don't know. Efficiency is very, very important. And now we're getting it for free, right? All you have to do is write down what you want. We didn't mention Nana anywhere. We didn't talk about, where we have to break or where we have to fork or anything, right? This code is figuring it out for you, right? And so I'll walk you through a little bit. So this is probably the first read. We can go and dig in, but for now I'll keep you at a higher level. So here's the first read. Then this gets executed. All right, this is an assign, so we set it to some variable. All right, this is the other assign. Okay, this yellow over here is the overhead. Right. So there's always going to be some overhead to join these processes. None of us like having leadership above us, right? And we refer to them as overhead. Sorry, leadership, okay? But there's some management that they have to do, right? That shows up as this yellow color in DAS, okay? So this is writing to the disk and then also a write head. And this is effectively bookkeeping the transactions for us, right? And then over here we have a transfer. This is that join, okay? And then finally we have a head, which is right here. You see that? And so this is the caching. They're bookkeeping this operation to let us know that it happened, right? So if were we to do it again, so it's happened, but I have to kind of zoom because we were at a certain frame. I think that's up, yeah. I think we can also zoom out here, or I can go to, let's go here. And we'll come back to tab. Yeah, okay, so this is the one that just happened. So we'll zoom, scroll to the right. All right, so now you can see, you know, it looks like it happened all at the same time, but as we drill closer and closer, because we're so far out, right? It is in fact happening, there's quite a few things happening, right? And you can see that we have, a similar setup. The two reads happen at the same time, right? There's an assign, the merge. Over here, we also had, this is most likely the assign. Pull this up. All right, the assign, the merge head, and then another head over here. All right, so merge head and then head over here. So we got all that for free, right? It's like remarkable, right? So, and I'm showing you this not only so that you can see how incredible the execution engines are, right? I mean, it's astounding that this level of programming has become free, right? I'm also showing you this because while Spark has the ability to do the same thing, it doesn't render it nearly as well, right? So in Spark, what you'll see is that here's a job and it executed, and here's a job and it executed, but you can't see the execution. We call this a flame graph. You can't see the individual pieces in time in semi-real time like you're seeing it here, right? Now, is this useful? Is it something that's a deal breaker? No, because in practice, you'll see this stuff is flying all over the place. But I think to help understanding, and also, when you're going through and developing, I check it for two reasons. The first reason is I want to see what could have been broken up. I'm curious to see what the algorithm comes up with, right? And the second reason is I just find it really beautiful. So, I have weaknesses, okay? So this is one of them, right? So, okay. So the other thing that I wanted to show you is what happens when we run this thing on a lot of operations are running in parallel, right? And so that will give you an idea of what an efficient graph looks like. So, intuitively, let me pose it to the class, right? So what you're looking at over here are operations over time. This is in milliseconds, right? So what would a poor execution graph look like? And what would a good execution graph look like? Can someone tell me what a poor one would look like? What do you think would happen here? Give it a minute. Spin your wheel. As you're thinking, I'll sort of recap what we have going on. So each of these are processes. Go, did someone say something? Yeah.
Yeah, so I think it's going to take longer because here you're going to have that first one, which took like, I think 59 seconds, you said. So you're going to have a cumulative sum instead of a broken down sum. So it's going to take longer instead of shorter because here things are happening in parallel instead of turning it into a sequential. So the times are going to add up instead of the time being from, let's say, this is about 500 to 780 milliseconds. Yeah.
Yeah.
So you're going to have a much longer duration instead of a shorter duration.
Yes, that's right. And so, William, what does that look like graphically? So William has given us the analytical answer, right? He's telling us that the duration of these processes are going to go from 500, right now it's 500 to 780. He's saying that a poor execution graph will be from, say, 500 to maybe more than 780, right? So, so use your eyes now, right? take away the analytical of this, right? What do you think the graph will look like? What will this execution path look like?
Maybe like 1 over X. And then
Say it again.
I was thinking maybe like 1 over X kind of going, starting up and going down like an L shape almost, perhaps.
Okay. So what will happen with these spaces? What will you see? Like,
Oh, like maybe like some jumps
yeah. So
or
you know
disturbances.
what? Say it again.
I say, or maybe like some disturbances, and it's not gonna be a smooth
Yeah. So
graph.
let's actually see what it looks like, right? So if we did this first come first serve, traditional programming, right? So let's. I'm going to take a screenshot of this for you guys. Well, okay, fine. We'll take a screenshot of this. And the snipping tool is somewhere. Okay, there it is. Yeah. And okay, there it is. All right. So we have this, and I'm going to take a screenshot of this. Okay. All right. So we have it. All right. I'm going to move this to a different screen, but we've got it. All right. Now, if we go back, right, and we run this all first come first serve, right? Here, here, here. And there's a couple of ways to do this. You can also do dataframe.compute if you don't want to output. That does the same thing, okay? But I'm going to just do it through head so we can see it through the window as well. Okay, and then I think we ended with this merge, right? Okay, so let's run all this again, all right? So from the top, I'm going to do this, 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 this. Okay, so it's executing. All right, and so it's done it, but I'm going to zoom out because the window is, we had zoomed in. So we got to zoom in and out again on this. Let's go back to task. Okay. Okay, so now let's do this wheel zoom. All right. Okay. And let's see, the big question is, where are those reads? Because those take the longest, right? There's a read. Let's keep zooming here. I hope this is the same execution one. So I have the screenshot, so let me look at that. Yeah, there's red and then blue, so let's see. This is different, okay. And so it still broke it up, right? But you can see there's some more gap, right? It's interesting that it's done this as well. And you can see there's some weights here, right? And so the idea is, certainly you want to see things running and you want to see them in parallel, so multiple workers, but you also don't want gaps, right? And ideally, you want this to be full. Like any white space is bad, right? So over here, let's see, you know, ideally these things that were running later, this could have moved forward or it could have been more compact with it. And I'll show you an example of that. Okay, so now I'm going to remove these heads here. I think also, let's try it with persist, right? Because I think that makes it more, that caches it all together, right? So or it might be BD. Client. Persist. Okay. So this actually caches it, right? So now I'm going to do the collection, right? So let's do data, right? And I'm going to do this for both of the reads. That's there, and let's do it for this one as well. Okay, and then we'll run this one more time. I'm going to jump out so hopefully we can see it go in real time. Okay, current graph, all right? So let's try this again. All right, so here. Okay, so we see 2, right? And there's quite a few operations happening in here. Let's wheel zoom for it. Here's to really get in here. Okay, so there is, right, okay, here we go. There's head, read CSV, read CSV. All right, so this forces it as well, right? So there's some parallelization that can happen even if you call for it, because we've asked for a little bit of the data set. I think that's what's going on here. But if you call persist, which basically caches it, that's what would happen had you actually executed the entire operation, right? And you put it in memory. This is the example, like if you were in pandas, right? And you ran this operation, you would read the CSV, you would then execute ahead, and then you would read the next CSV, right? And you can see there's all this white space. There's all this time that's been lost, right? And I view that as, the analogy I use is you have a child who is just sitting, a child that's bright, right? Who's sitting in a room, by him or herself, doing nothing, right? They're not, playing, they're not reading, they're just, sitting there sort of idly, right? And you don't want that. You want them to be doing something, right? It's wasted cycles. So same idea here. Okay, so let me, all right, so I'm going to remove this, and I'm going to remove the other persist, okay? And I'm actually going to restart this because you can clear out the memory, but it's simpler if you want to remove persistence points to start again here. So, all right, so we're going to get a new client. And then I'll take you through an example of how this looks when it's going really fast. And then we'll jump to the same example in Spark, right? So you can see what that looks like. And okay, so let's refresh this. Sometimes it takes a second because the process went out. Okay, now we have it. There's tasks, nothing's happened. All right, so we were here, and I'm going to kind of just blast through this because we went through this yesterday. But I want to take you to a special, right, so you're starting to see things executing in parallel, right? And we'll get down to the machine learning section of this, right? So let's keep going. We're joining the fundamental and the stock data together. We get the next day. We take head on that, all right? Okay, and all right, so then we do the next day. We're taking head on that as well. All right, we're merging that to get in the, we figured out what the next day is. We're going to go get the stock data for the next day, right? We're trying to figure out what happens the day after earnings are released. And we're going to calculate the diff, okay? We're going to calculate whether it went up. This is that labeling, okay? One more head. And the graph should, okay, there goes the graph. Okay, and you can see it's executing this whole shebang all over again, right? So each time you call an operation, it's running it from the beginning, right? That's why you see it, these chains, right? Even though I call it, like, watch this. I'm just calling head on this data frame. But all of that happened, right? And even though you're having to replay from the beginning, right? At this point, you have not read in the file. When I hit head, Dask has not read in the file, but it's finding the fastest path from that operation to where you are now, right? And so for small programs, sure, you can run in series and you can get out quickly. But chances are, if you have multiple data sets, you can read them in independently, right? And then it's only when you start joining things that they have to come together. But even there, the optimization engines can figure out the best way to do that, right? Like we've not, put in a point that says we have to be in series yet, and it's figuring out how to do this, right? Okay, so so almost there, and then we set the labels. Okay, we get the features. Okay, then we have, we print out X one more time to see what the independent variables are. Okay, good, so the graph is coming out good, that's good. And again, here's an assign, there's the read CSV again. See, we did this, right? But let's see what this is, this process is. This is a head. Okay, yeah, so there's the call to head, okay? And now we're just doing some bookkeeping for the figure sizes. Okay, we're saying Y. I want to see the dependent variables. And again, we just called head and all that happened for us. Okay? And so it started from the beginning, right? But it is intelligently figuring out how to get there as fast as possible. Okay? All right. And all right, so we're going to look at X one more time before we get into the machine learning side of this. All right, and here we go. Okay, so as mentioned, yesterday about this, you can execute if you're in Dask, you can convert back to pandas. That's what this does. This compute call converts you back to pandas. All right. The problem is you have to have the memory locally to do that. All right, if you don't, you're going to run out of memory. The system's going to crash. Okay, so I'll take you through an example of us doing that. All right, so if we do that, okay, no problem. Now you're in pandas. All right, and we're going to run this 70 times. Right, 7 runs, 10 loops each. So it does it 7 times, gets an average, and then it does that operation 10 times. All right, so effectively 70 runs. But an average of the average 10 times, okay? So, all right, so it's going to do this, and you'll see that, there's some execution happening. Let's see. All right, so it does that, all right? And this is all in pandas, so it doesn't show up out here, all right? This is just the Dask execution, okay? So, and it did that in 8.87 seconds. So it's quick, right? Pretty quick, all right? 70 operations of fitting the decision tree on the data we have, all right? Now you can do the same thing, but this is with Dask, all right? Did we get this far yesterday? Did we get all the way through the notebook?
I think we did, but it was pretty fast, and so you said you go right to today.
Great, thanks, William. Okay, so so now what's going to happen is we're going to run the same thing, but see, we have little x over here. That's the pandas data frame. Little y, pandas data frame. X, capital X and capital Y are Dask data frames, right? And this is one of the big differences between Dask and Spark, okay? When you are in Spark, you need to stay in Spark's ecosystem. If you want to do machine learning in Spark and the data is gigantic, you cannot come back and use sklearn, right? You have got to use, because sklearn takes pandas and Dask data frames, right? Really, it accepts pandas collections and Python collections, right? And that means that there has to be this mechanism where it appears like it's in memory. Dask implements the API, so it works, right? But if you, and you'll see this when we go into the Spark section, Spark is going to have its own machine learning routines that deal with Spark data frames, and they're pretty good. I'll say they're not as good as sklearn with Dask, right? But they get the job done. There's k-means, there's decision trees, there's random forests, there's regression, so that they have these things, but it is nowhere near as intuitive, particularly with visualization, right? So once you want to visualize this stuff, there's no clean way to visualize a Spark data frame. you've got to convert to pandas, right? Or maybe you convert to DAP, right? But there's no way to, and maybe that's the way out. You could do it in Spark and then come to DAP. But straight Spark, you'll see, is nowhere near as intuitive, and you must use their library. With DASK, you can leverage all of pandas and sklearn, right? This is the big leap with this, right? So we are going to, over here we did this in pandas, we're now going to execute a fit on an sklearn object, right? And this is straight sklearn. You cannot do this in Spark, right? We're going to execute a fit on sklearn decision tree with a DAS data frame, right? And we're using the back end of DAS. And so when you do this, and we're doing it 70 times, here comes the fun, right? So usually this thing, yeah, see, so it's running, and it proves it, right? You're executing all these operations within sklearn with DAS data frames, right? It cannot be done with big data this way with Spark, okay? And so what this gets you is the ability to basically treat it like it's Python. You haven't really done anything wild, right? And I think this is one of the big reasons why Dask for machine learning is very important, right? You can leverage the existing API. And they do need to do something to catch up to Keras, and I think they're working on that. But, and so look at this, right? I don't know, I'm a fan of color, okay? So we ran this thing 70 times, and let's wheel zoom for it, right? Look at how it has, just cut up everything for us, right? Like, so you have from the very beginning, so the read CSVs, then, the assigns, merge items, everything is in here. And this is an example of, obviously I looped it, right? But if you had a long running program with a bunch of steps, you would hope to see something like this where, there's stuff going on as much as possible in parallel, right? And there's minimal white space. Like this thread over here was working really, really well. No, like very few wasted cycles. This kid is being exposed, right? This kid is not being as exposed, but all the kids are getting some exposure, right? So, okay, good. Any questions here? Okay. Key takeaways: memory and parallel algorithms, and the ability to get these parallel algorithms to work for you for free is what is making stuff go fast now. That's the breakthrough, right? You did zero coding for parallel algorithms, and you got parallel algorithms on the ability to scale to whatever size data, right, for free. Right? That's the big leap forward. Even with quantum, it's only because quantum has the ability to store that much more, so we can do that much more in parallel because we can keep track of the bookkeeping and the call stack. Right? Good. All right. Let's take a break. Let's do 12:35, and then I'll come back and I'll show you how all this stuff works in Spark, and answer any questions, and we'll go from there. Good. All right. I'll see you guys at 12:35. Mute. Did everybody hear me? Good. Thanks, William. All right. So we've seen it in DAS, right? Now let's take a look at this exact same example within Spark. So we'll go through this. I'll talk about classification models in general, so you can see, how this works. You'll see two examples of it here. Then we can get into internals, and then I'll share some tidbits from the target story as well. Right? Okay, so first, a little bit about Spark. Right? So if you look at Google Trends, thanks, William. Yeah. So you can do, let's do DAS. Right? And so this gives you, Google calls this interest over time, and so highest point in the chart for a given region in time. So it's the peak popularity. So they don't tell you like how popular it was, but this is the time when it was very popular, okay? So, but you can get some idea if you run a comparison on it, right? So if we then say Spark, right, you can see that Spark, at least the term, these terms in general, Spark is, much more popular, right? This is like, nearly, less than one, right? So Dask is not as popular as Spark. But if you get more specific, let's say we say Dask data frame and Spark, so sorry, I got to do one first. So Dask data frame and Spark data frame. It's a little bit better now, okay? And here you can see they're saying insufficient data, but they're giving you some type of projection here. And it, still.
So my phone just gave out, but can you hear me now? Good. Is this better, or was it better the other way?
This clear. I think it's.
This is
I think
good.
you can
All right,
hear
good.
it. Yeah, this clear.
Okay, that's good. All right, so let's put this to charge. Always good to have a backup plan. All right. So we can see that Spark is still more. Thank you, William. So Spark is still more popular, right? But Dask is on the move. So much so that, again, we're moving our operations towards Dask. But if you have a Java shop, you need to, still consider, you still need to use Spark. Okay, so let's walk through this, right? So the first thing is the setup is much more complicated. You've got to do some installs for Find Spark. You've got to do, and these are pip installs or conda installs, right? So these packages need to come through, and that's one thing. But you also have to have Spark installed locally. And what that amounts to is you're going to need Java, you're going to need Spark, you're going to need the conda packages you have, and the depending on your distribution, you don't need Hadoop, right? Because Spark packages it, but you've got to get some environment variables set. So I'm just curious, right? Who in the audience has set environment variables on their computers? Besides the supercomputer scientists, is there a raise your hand feature in WebEx here? I'm trying to see if that can happen. So if there's a way to raise your hand or flag, Nana, is that possible?
I've seen it somewhere, but it may be Zoom. Something. Let me look around. Yeah.
No, and that's fine. So we can just do it audibly. So If anybody here has set an environment variable on their computer before, speak now. Yeah, okay, yeah. So this one says yeah. Oh, okay, there's a smiley face. Okay, so do the smiley face or put it in the chat window. Let me see if I can get it the chat window. You can also add it in the chat window, right? Thanks, Sheila. So I'll pose the question. Has anyone set environment variables? Here. Okay. And then the second one I'll say is, has anyone done pip or conda install? All right. So if you've done environment, you can write E in the chat. All right. And if you've done pip or conda, you can just write P. So E is for environment. P is for pip/conda. So I'm very curious to see what this distribution is. Yeah. Okay, so we have a couple of folks. Yeah. Yeah. Okay, yeah. If you've done both, you can write PE if you want. Yeah. Yeah. Okay. So it looks like you can go ahead and fill out, but it looks to me, and just from my experience teaching the subject, even to data scientists who are in the field, very few of them have dealt with environment variables, and that is because pip and conda make it so easy, right? So the other thing you'll have to do is you'll have to set environment variables, and it depends on where you are. So I'm curious, who has a Mac in the audience? You can just raise your hand, or you can write M or something. Yeah. Okay, Sheila's got one. That's good. Yeah. So okay. So it turns out that getting Spark working on Mac and like basically any Linux or Unix servers is much harder. And what I mean by that is you have to learn how to maneuver at the command line. So Sheila, have you ever had to like maneuver at the command line and set like environment variables and flags? Yeah, okay, good. So, and it's not so much fun. So I'll give you an example of what this looks like, right? So, so you have to basically go to your home directory. So you have to learn how to maneuver, okay? And then you'll have something called a bash profile. And I use this thing called VI. Who knows how to use VI in the audience? Okay, yeah, so us older folks, right? We know how to do this, okay? So, and VI is like a different world. Like you can't just type here. You have to enter in shortcut keys to get the ability to edit and whatnot. And so it is unfortunately implanted in my brain and somewhat natural now. I wish I could forget it, but it's there. And so you can use things like Nano or TextEdit if you're on the Mac as well. But you see, we have, I think mine may be in, maybe in a different bash file. Let's see this. So, because I'm on Windows. Okay, so even though I have a Mac, I have a Windows machine, but I have the git prompt, which makes things look like it's Linux. So I can do things like LX or LS, which is similar to the Mac. But the short of this is, if you're on Mac, you would have to go in here, and you see how I have set this variable here, this PS1, right? That's what makes my prompt look, I don't know, archaic, okay? And so 80-ish, okay? So you don't have to understand what this is, but if you were setting up Spark and you're on the Mac, right, you would have to come in and do something like this. You'd have to say Spark home is equal to the directory that your machine that your Spark installation is. So let's say you had it in I don't know, home. Let's say Sheila Spark, right? And so you'd have to do this. You have to set it in this file, and then you would have to export it, right? And so you've got to do some. Well, it's actually here now, right? So it should be set. So if I do right quit, and I source that profile, okay, and then I do echo. There you are. Okay. So like my computer now knows where Spark alleges to be. All right. So, but that's a lot of work for someone who doesn't maneuver at the terminal. Okay. So it's okay for me and some of us old Linux guys or gals, but it's not conducive for everybody, right? So that is why, yeah, you can use Notepad Pro or you can use GVM. Very good points, right? So so that's the first barrier. Okay, the second barrier is that you can't get back into pandas, as we saw. But more often than not, I find the installation barrier for Spark to be, even if you get through it, you're like, why did I have to do all that? Like, it should just be like this, because pip and conda make it like this, right? So, all right, I'm just going to fix this bash profile and then we'll get into it. But I needed you to see and somewhat feel what goes on, right? So, clear. Okay, so now let's go back to this notebook, all right? All right, and I'm gonna move the chat window out. All right, so same type of thing. We're gonna get a Spark context. We're gonna get a Spark connection, okay? So now we have a Spark connection, right? And what happens is the Spark runs in its own process, and you have to connect Spark to Python, right? So if you wanted to build a classification model and you had a large amount of data, or you wanted to take advantage of Spark's parallel execution, you would have to use this thing called PySpark, okay? PySpark is basically an interpreter between your Python process and the Spark process, okay? And so so you can, follow the setup for this. You basically set it as what the name of it is. You could have called it whatever. We could have called it VADSTI. And then you're setting the master point. If you're in production, you would set it to some URL, okay? If you're just doing development, you can say local, and then local here, you can specify how many cores you want to have Spark use. And so here we're saying to use 2 cores. Same setup that we had when we did this with Dask, right? Okay, so, and then we're going to tell it how much memory we want it to use, very similar to how we did this with Dask. All right, so we've done that, and then we get some output telling us where we are, and what version we are, and then we have a Spark kernel. I mean, a Spark instance. Okay? All right, so, and technically this is referred to as a Spark session, right? So you can have multiple Spark sessions, but this is, imagine this is like a connection to the database, right? But now you're talking directly to Spark. Very similar to how we had the client talking to Dask. Okay, so we've done that. Now we're going to read in that same file, right? Okay, so it's trying to read it. Okay, there we go. And we timed it, so we have this file, okay? And what's happened here is I'm calling cache, right? And this is the same thing as calling persist, right? But you don't have to, okay? And I actually advise that you don't, but there are times when you want to, right? So for example, let's say you're building this out and it takes 10 minutes to read in this data. Okay, so every time you run this cell, 10 minutes, right? if you don't call cache after you run this, then when you execute another operation, like say when we do a join down here, right? This is a join. When you do that, you're going to have to pay that 10 minutes again, right? And let's make it worse. Let's say it's an hour. You don't want to wait that much time. So if you don't want to wait and you have the resources, you can call cache, right? And what that does is it basically takes this read operation and it puts it into a data frame and stores it in memory, right? So now it is in RAM, right? Same thing that persist would do for us. And what that means is it doesn't have to go fetch it, right? So now when it goes to get this, when it goes to reference this data, it's just going to access the memory location in RAM. So it's fast, right? And it doesn't use the Spark engines anymore. So you get the benefit of not having to execute it all over again. And it's stored locally for you in RAM. But the problem is you no longer get the optimizations of parallel execution. So if you catch everything, right, then everything is going to run in series, right? That's the cost. You're fast, okay? You're no longer going and doing the operations all over again. You're fast, but you are now 100% in series, okay? And in practicality, what happens is, let's say you build this notebook and it's fantastic and you're using it to run some process. Well, you get it worked out and then you run the notebook, right? So if you're just going to run the notebook from start to finish, that's how we do these things. And the final output is a file or it's a message that's sent, whatever you choose. You don't want to run caching then because you want the fastest execution through, right? You want to be able to run in parallel, right? So the optimizations can be made. But as you're building, you can use cache to debug or to run fast if you're okay with being in series. Okay, so, and also, and this is the same thing. So data.show pulls some of the data back. And so all right, so we have this data frame, right? So if you do a show, immediately that pulls back the data, right? And then if you do a cache, that says put it into memory. I don't want to have to run back to disk again, right? And so, and then what you do is, in order to reference this is the Spark magic, okay? In order to reference this data frame, this set of data, which is the Tesla stock data now, okay? In order to reference this later in code, you have to create a temporary view, okay? And I'm going to just call it the stock ticker, right? So you create this temporary view, and then when you want to execute SQL, you can reference it by just saying TSLA, okay? Another thing to note is that the show from Spark, and maybe I've grown a case of like vanity. I don't know. Okay, like I would say that I'm like visually starving for new stimulation because of this whole situation, right? But I find the output of Dask's data frames to be much prettier to look at than the output of Spark's data frames, right? So, but that's aesthetics, right? So, okay. So, all right. So we have this, all right? So we have this, now we have a reference to this data frame with the stock data in it, right? Open, high, low, close, adjusted close, and volume. Great. So we're going to do the same thing now for reading in the fundamental data for Tesla. Okay, and the job algorithms work the same way. Spark will put it in parallel for you as well. You can't see it as cleanly, but it'll tell you that the jobs are executing, right? All right, so we're going to do that, right? So we get the fundamental data, same idea. I'm caching here just so that we're quick in case I need to reference this again, but you don't have to, okay? Again, in practice, you will not. And so, but this is something interesting. You can do the same thing in Dask and Pandas, but it's a little bit easier, I think, in Spark. When you do a show, you can specify that you want to be vertical, right? And so like over here, the reason that makes sense is over here, when you put out the data frame, we had 7 columns, right? So it's not overwhelming. Yeah, you can see all the data at once, right? And it's still only a clip. I think this is the top 20 rows. Yeah. And yeah, okay, top 20 rows. But what happens if you had 100 or let's say 50 columns, right? So if you have that many columns, you'd be paging off to the right. And they both like to do this ellipsis thing. So you would get like the first 7, you get ellipsis, and then maybe the last 7, right? And then you're like, okay, well, where's everything? And you have to set parameters to get at it. Okay, so to avoid that, you can say vertical equals true. And what that does is it gives you all the columns vertically, right? So, you would have seen this horizontally, but now you can see it vertically. And, I said, give me the first 1 row, but let's say you wanted to look at the first 2 rows. Okay, so here's the first row, but it's being displayed vertically, so you can see all the columns, right, without having to page off to the right. And then you can also see the next record right below it, right? The columns get reprinted again, and here are the values. Right? So when you have a very large set of columns, you can view it this way. Okay? All right, so now here's where the SQL inside of Spark comes into play, right? So Spark's most popular library is Spark SQL. Okay, and when we did a join for the fundamental data back in Dask, we did this with a merge. Okay, so that was here. Next day and date. So when we joined fundamentals, we did that here, right? Date and quarter end is where we joined, right? So this is, pandas and Dask syntax, a Pythonic way to do it, right? Spark says, they can do that too, right? But it gives you an opportunity to write SQL, right? And not only that, if you have existing SQL, which is quite complicated. I mean, I have SQL that, I've seen SQL which is 3-4 pages long, that if you had to translate into Dask or Python and pandas, it would be a considerable effort, right? But with Spark, you can basically paste that SQL in, and it will manage it for you, right? Like and you'll be able to execute it across this data set as long as the column, the tables you've created have the same names, right? So, but the key thing here is when we brought in the fundamental data set, right? We called it fun. That's the nickname we gave it. And when we brought in the stock data set, right, with just the high, lows, and closes, we called it Tesla, right, TSLA. So when you join, you reference those aliases. So we're going to do select star from Tesla, right, where F and as select star from Tesla as T, and fun as F, where t.date equals f.quarter end, right? And this is all made possible by the fact that those aliases map to these names, right? And so now you don't have to learn Python libraries, you don't have to learn how Dask does merges. If you understand SQL, which most database engineers do, most programmers do, almost all data scientists do, you can just execute it this way and you get the same results, right? And in fact, there are things like subqueries that can be executed here that are much more difficult to do in straight Python and merge operations, right? So, okay, so we do that, and we're moving on. And so you get, I'm printing it out. We have the date, right? Open, high, low, close. Now we have the we have stock data mixed with fundamental data, right? And now we're going to get the next trade date, okay? And this is the other thing, okay? So when we did this in Dask, right, you had the ability to use Python functions to get the next date, right? When you do it in Spark, it is Spark, right? There's no like messing around with this. You have to use Sparks with column, so that you know how back over here when we said let's assign a column called next day, right? The Python syntax for that is you just say the data frame name and next day, right? You create this column and you assign into it, no problem, okay? In Spark, you use something called with column, okay? So with column is saying, all right, take this data frame that I have now, add in a column called this, and I want the calculation to be this, right? And so you're adding a date, right, to the column called date, and you're adding one date to it. That's how that reads, right? But if you notice, everything is this F, right? So Spark has this concept of these row functions, right? And so what it's basically saying is for every row in the column date, right, I want you to add it, right? This is how you do row by row operations to fill out a column, right? This basic syntax, I'm going to say, is not as intuitive as that, right? Like that is like just basically, I mean, you have to give it to the Python and the Pandas folks, right? So, but it works. Okay, they both work. All right, so this is how we get next day. And then what happens is you can continue in the fashion that we've been doing it. You can continue with creating new data frames. And so this puts it into a new data frame, but I want to be able to access it via SQL because that's the big upside, right, of being able to use Spark. So every time an operation occurs, we're going to set it as as an alias so that we can reference it in future queries. So now we have next day. And so over here, we're going to select, okay, so there's next day, right? And so now you have to go back and get the stock data for the next day, right? And so all that is, you know, you can select n.star, and t.date is n.date. And so these, don't worry about this. So you're selecting some columns, and that happens because you're selecting from next day, which you're calling n, and the original data set, which you're calling t, right? Where the next day equals the date in the original data set. That gets you back the open, high, low, close, right? And so, and what you're pulling now is every field from next day, which is the stuff that the fundamental set with the original Tesla data, right? You're pulling in the date from the stock data as end date. Now that's important, right? So the new date, right, that's coming in, because you're joining these records, you're going to have a couple of dates. You'll have the date from the original stock transaction. So you have this date, okay? You have next day, right? You have the quarter end date, okay? This is where you are right now, okay? But you also, when you join this, right, you're going to be joining it with a table that has these fields in it, right? So you're going to get another date column, right? The date column is going to come back. And so to avoid a collision here, right, you can rename, otherwise Spark will give you a default name, but you can rename that incoming date as, say, something else. Like I called it end date for just new date, right? And, you know, I know that you're going to have a new close, so I set it as new close because I want these two dates also to be unique. Right? So, all right, so when we do that, we'll get these columns back and we'll look at end date and we'll look at end close, okay? Right, and so we're going to save this as next price. Right? And so that's what happened, right? We found the next day, and then we found the price of the stock on the next day. So we do that. So there's date, okay? So that's the original stock data, the fundamental data that we joined, okay? Then we have the next day that we calculated, all right? And we took, so remember, we took all of the existing data in next day, and we pulled end date from the, we pulled date from the stock, original stock file, right? And we called it end date. And we pulled the close from the original stock file and we called it end close, right? So we're slowly building up this data frame with the information we need, right? So next day and end date are the same, right? This is just me being cautious by adding a field, making sure that it is in fact the same, right? I like seeing them close together. I have this, quirk about QA. So, but either way, right? So now we've got the fields we need, okay? So great, so we have that. And if you wanted to, the next thing we're gonna do is figure out the difference, okay? And here, you could execute this through SQL, but it would be painful, right? So here's an example of where you're using Spark methods again, right? And so again, you're going to create a column. That's the width column. Pandas, you just put it in brackets and quotes and give it a name, right? Here you do width column, and you specify what you want to call it, okay? And then you specify what columns you want to compute with. So I want the column new close and the column the old close. Okay, and I want to compute their percent difference. So I'm going to subtract one from the other and divide it by the old number, right? And that is going to store that inside of this diff. And this returns a new data frame that we're calling, that is variable named diff. We cache it here because we're basically in debug mode. And then we create a view for it, and then we want to see it, right? So, yeah, and you could execute all that through Spark SQL, but it's much trickier. I mean, all through SQL, but it's much trickier. So, okay, so we do that. Okay, and now we should have the diff, right? So for this record, it was negative, so it went down, right? For other records, it went up or down, right? And then the same thing we did before in Dask. Now we're going to say, all right, we need a label for this classification model, right? We need to be able to say, what is it that we're trying to predict, right? And so sometimes you have the label, cancer or not cancer, right? Death or alive, red or green, okay? Sometimes you don't, okay? And so it's a mix for us because we're trying to create a prediction on whether it went up or down, and there's no already calculated field that does that. We had to create the label, right? And so, so we're going to create that label here, and this reads same thing. We want a column called went up, and we want to use, now here's again Spark magic, okay? So instead of saying mask or loc like you would in pandas, you say when, all right? Because otherwise, if you look back over here, we've been doing assignments. We just use this f column. So here's the column name, and whatever's in here is what's going to get computed in this little, after the parentheses, right? So over here, what's happening is we're going to calculate this, right? But we use this when to say, if the difference is greater than 0, so if the percent difference is greater than 0, put a 1, right? So that's 1 is it went up, all right? Otherwise, 0. All right, now it may be a little bit more verbose, but I will say this in Spark's favor. Spark documentation is superior to Dask documentation. It's not even close. I mean, Dask has made improvements, right? But Spark has been, major and running for like a decade now, right? So you can get ways to do this much, much faster in Spark. There's no way the Dask developers can cover all these cases well, right? They're working on it, but they're not there. You know, a lot of this, and okay, and in fairness, how many times when you're creating a notebook do you go and read the docs as opposed to just going to Stack Overflow? Right? Stack Overflow has a question just like yours. And so this just has not bubbled up as much in Stack Overflow as it has for Spark, because Spark's been here that much longer. So they'll get there. Stack Overflow or some other site will eventually have all these combinations. So, all right, so we're going to create the label, okay? All right, and so now we have whether or not it went up, right? So this one was negatives, and so we set it as 0. That's the otherwise. All right, and here's the big one, okay? At this point, if you want to use sklearn, you have to come to pandas. Now, we're going to do this without going to pandas later in the notebook, all right? But if you want to come to, and you want to use sklearn for the visualization or whatever it is, you've got to make sure that the data set is going to fit in local memory, right? This data set is small, so this works, right? So even if your data is not gigantic, you can still use Spark or Dask because you get the benefit of lazy evaluation, which really means the evaluation is going to be much faster than anything you could code, right? And you get the benefit in Spark of writing SQL queries. So let's say that you're not so fond of pandas and all the operations they have, and Dask, and you are a SQL Jedi. So great, you can use Spark and execute SQL against the data set. And I can tell you the COVID model that we built, right? Yes, it has a lot of data, but not so much data that it won't fit on a single machine currently, right? And that ingests the world's data for COVID, okay? Like as far as deaths and infections, right? And so there's quite, I think it amounts to like the 30, 40 gig of data, okay? That fits for us on a machine because, the machine will page to disk and it's not 30, 40 gig all at the same time. It's 30, 40 gig over everybody. That model was built using Spark to cut the data sets up the way we needed to. Because there are some operations, yes, we could have done it in pandas, right? But there are some operations like unions and intersections and subqueries in particular that are just much better, much easier to execute in Spark as opposed to pandas or Dask, right? So like our most successful model uses Spark to do all the feature engineering and putting all the data sets together because it's that much simpler to do some of these complex operations, right? Okay, so, and then we then come to pandas because it fits in memory and we run, some analysis on top of it as well. So this is very common, right? All right, so you've seen it in pandas. This is exactly the same way. And so, in the interest of time, I'll kind of blast through this, but I want you to see what happens if you stay in Spark, right? So this is the same stuff that you've seen in the other notebook. It's going to render a decision tree. Okay. There's the fit. You've got it. Yeah, okay. And there's the decision tree. All right. Okay, great. Now, the last thing with Spark, you don't have to leave Spark and come to pandas. You can stay in Spark. If you have a lot of data and you're building a classification model and you don't care about this nice visualization, you just want to get a predictive model in place to say, when this data comes in, what is it? Is it, are we predicting that it's going to go up or down, right? Based on the fundamentals. And that's what this is saying, right? Like it's saying if you feed this data and the non-controlling interest is less than this number, it's going to predict that it goes up. And if you feed it, and if it's more than this number, right? And current assets is less than or equal to this number. Actually, if that's false, right? No, if it's less than or equal to this number, then it's going to say that it went up again. Otherwise, it's going to say it went down. That's what the prediction engine will do, okay? So you don't really care so much about this visualization, even though I find it very beautiful. Okay, and I have a weakness for this stuff, right? But the rest of you may find it fickle and not important whatsoever, and that's fine. Okay, so you can do the same thing in Spark. It's more complicated, but it's there, right? So I'm sorry, I missed some of these questions here. Can you write to disk and then use DASK? Yes, you can. You can actually mix and match this all the way through. But yeah, and that's an idea too, right? Like you can send Spark into DASK, and then there's another question: will Spark shell have access to your Python Spark data to write the SQL statements outside of the Python station? Yes, absolutely. So the Spark shell, you can access. You can execute SQL commands at Spark shell as well, right? And they just basically go in variables, right? So the Spark shell is like a Scala interface, right? And you can also have a PySpark shell, which you can execute lines of Python in as well. If you can tie to the same session, yes, right? You'll be able to get at it. Yeah. Okay. So, all right. Now let's see here. Okay. So, all right. So how do you do it if you want to stay in Spark? Okay. So Spark is like anti-visualization. They could care less, right? And I understand it because it's if you have a complicated model, the decision tree will likely be uninterpretable, right? Depends on how many variables and how many combinations you have, but it literally looks like the screen is melting at points, right? So very much like that task graph when we have so much going on, like it's there, great, we know that there's some order and things are executing, but without closer inspection, it's uninterpretable. So Spark takes the approach of it's too much. You're using us because you have a lot going on, so don't even try to look at it. Okay, and they do that by indexing everything and treating everything as a vector. If you were to talk to not Vernon Max, if you were to talk to Maxwell, or if you were to talk to the physicists in the room, they would tell you that everything is vectors, right? And that's because everything is really multivariable. It's never single variable, right? We can have functions of vectors and functions where y equals x squared. Sure, but it's really y1, y2 to y whatever is equal to x1 to x2 to x whatever in some phenomena, right? It's never single variable in and single variable out. It's very, very, very rare. Multivariable in, multivariable out. So the concept of vectors is used, right? And what we're doing is we basically take the features we had, okay, and we vectorize them. So what does that mean, right? Does that mean we like eviscerate you, or we beam you to through a transporter, right? It's not that at all. So let me walk you through an example of this, right? So you have this is the Spark data you had, right? And once you vectorize it, I'll show you what this looks like. Oh, I didn't run this yet. So let's run this field, this cell, and then we'll run this cell. Okay, so it's coming. All right, so now what's happened is, and this is just because the Spark guys, I'm telling you, they must be physicists. They took the data that you cared about in your Spark data frame, right? So you cared about these features, assets, liabilities, etc., right? And they took those and they put them in an array. Ta-da! That's what vectorizing is, right? We take what you care about and we put it in an array. When you guys were dealing with Keras and TensorFlow and neural networks, you know what they do? They take what you care about and they put it in an array, right? And that is essentially vectorizing. And why? Because vectors are basically arrays. A collection of items that are related in some way, right? Okay, so So we vectorize it, right? So let's get you an array of what you care about. These are the values that we cared about for this row, okay? And then you can get all the vectors that we created. So we did this for every row, right? So if I wanted to see that, you could execute this. And so that data set we had before, which had all the columns with all the values nicely lined up, and then we had a column over here for went up, right? This is basically, you know, if you were to present this horizontally, let's do that actually. Before we go, let's just show that. So this is basically it. So if you had, this is X, right? And this was Y. So if you took this and just slapped it on the side over here, that is what you had before. Tabular version of the data set, right? The vectorized version of the data set is all of that condensed into arrays. It doesn't like columns, right? It doesn't like commas. It wants everything in arrays, right? So if you're going to deal with Spark, you have to get good at arrays, okay? And this is the same thing. So when we had goodbye columns, it depends on the ordering now that you've put through. It was 0, right? And you know, when it was what is it? When it was such and such, it was 1, right? So okay, so we have that, right? And then let's see this, right? So so we're going to select this. Okay, so we vectorize the data. One more time, punch out features. Okay, you see that. Now we do the same thing. This is just Spark. Everything has to be indexed, right? So you could have had went up as true or false, right? That would have been more natural. I like to use 1s and 0s for Boolean terms, right? But Spark wants to create its own labels for that. So you could have had like 5 different terms: red, green, blue, or it could have been it went down a lot, went down a little, stayed the same, went up a little, went up a lot. Right? You can imagine we had many different labels here. And if that was the case, Spark wants to make everything vectors and labels. It would index it, right? And say, okay, it didn't go up is 1, and it did go up is 0. That's what's happened here, right? So it's creating its own numeric version or key for each of our possibilities. If we had another one out here, there would be another key, right? And they do that because they want to deal with numbers. Right? It's very aesthetic. There's no room for aesthetics. It is fast and you know, very efficient. Okay. All right. So we do that. All right. And then finally, okay, this is executing. All right. So we have this label index, and then finally you can do the exact same thing we did above, right? And it doesn't look anywhere as beautiful or as interpretable, but it is working, right? Here is the decision tree classifier. It is a Spark class, right? And you're going to do a fit on the data frame that you created up here, right? Which has the features and the labels, right? And instead of using X and Y, you've told it, you know, since you patch in, you've told it what the label column is, right? So label index, this is the dependent value. And this is the independent values or features, and we've told it that. And so when you run it, you'll get the model. You can run model.predict on incoming data if you want to. But you can also print out the debug string. This is as beautiful as it gets in Spark, okay? And you will get, let it fit, and then it'll print it out. So it's cooking. You will get you know, if feature 0, right, which it's using by indexes over here, right, is greater than, is less than or equal to this value, then they go into this if, and if that's less than or equal to this value, then they predict this. Otherwise, if feature 0 is greater than this value, they predict this, and else if it's greater than this value, we predict that. So a similar output. Nowhere near as interpretable. You'd have to backtrack this to figure out which exact indices they are, but you can do it, right? So yeah, and that's how you see it in Spark. So we only have a little bit of time left. But I'm just curious now, okay? Who prefers Spark and who prefers Dask? And tell me why.
Yeah,
Or
I
are
think
both of them equally bad?
yeah, I think obviously Dask has a much lower learning curve, but Spark has a higher learning curve and a lot more capabilities, right? So you have access to your Hadoop file system, which you can also access via other languages that support that
That's right.
platform, right? So
That's
that's
right.
it. The only thing that impresses me, which I was just thinking about, is you get a schema for free in Spark. So when you dump it into a table, you didn't specify the schema. It gave you a tabular data with some schema behind. Can you display the schema? I mean, just as a
Yeah,
learning tool, right? Yeah. Can I
yeah,
just
you can.
take that schema and then?
So I think that's D types as well, right? So
Oh, the
yeah,
data. Okay.
yeah. Let's look at it. Might be types in Spark. Let's pull it up. I think it's types. Let's see. It might be. Let's see if it's D types. But you are correct that it gives you the right. So it tells you what the types are. But Dask now does that as well. Dask will give you the data types and the schema. But William makes a very good point. If you are on Spark and Hadoop infrastructure already, and a lot of places are, right? So, I mean, Google was built on Hadoop. Like, so they've got a huge, Hadoop infrastructure, right? And you need to get access to the Hadoop classes or Hadoop systems. Then you're within that ecosystem when you're in Spark, right? So, yeah. So it depends on what you have going on, and yeah, these are good points. Anybody else? Okay.
Yes.
Good.
Oh, I like Dash and Spark. The thing I like about Spark, however, it's more detailed, especially if you're someone new trying to get into this, to explain it in more depth. And you can also use Panda if you really want a visual with Spark. That's what I like about it. And I'm used to SQL as well. But I think I prefer Spark, even though I like how Dash looks. But as you said before, you can use Panda if you want a visual as well.
Yeah, and that's a lot of people are in the same camp, and the big thing practically for you will be the use of SQL, right? Because you cannot do that in Dask. They both have some flaws. Anybody else on this? Okay, let me leave you with one last thing. I'm gonna share my screen. So this will just take a minute, right? Because I took notes to shortcut it for you so that you don't have to. Zeppelin is great too. It's similar to the notebooks we use. Both are good, right? I just like Jupyter because of the magic functions and whatnot, but it works just the same. Yeah, and has a pretty good setup with Spark as well. There's an inbuilt integration. Okay, so let me share. Where is it? Target data mining. All right. And so there's a couple of things. I mean, I found this thing, outrageously important, but let me see if I can summarize some things for you. Okay. So this is how they talk, right? So soon you'll be buying cereal and paper towels from us. and keep coming back. Right? You need to think about that. Right? They have the intention of getting you to buy stuff and return and be like return customers, right? And that to me is like a drug dealer type talk, right? Especially how they've said it. Okay, so that's one thing. Conscious decision making shape 45% of the choices we make every day, right? Duke University. That habits, rather than conscious decision making, make up 45% of the choices you make every day. You think that's air you're breathing? Yeah. You need to think about that, right? Nearly half of what you do is based on habit, right? So can they infiltrate? Can they get at that, right? Okay, so there's that. And then, so they talk about how they examined the rats to figure out when they were vulnerable, when they could change the rats' habits. Habits cut both ways, right? If you have a habit that is in their favor, great. But if you have a habit that they want to break, we don't want you to shop at Walmart. We want you to shop at Target, right? How do they get you to be weak? Okay? So that they can break that habit, right? How do they incentivize you? And they used mice in a lab to figure this out, right? And it's pretty amazing to me that this stuff even happens. And then there is another piece that is really important. Yeah, there's anybody use Febreze? Nobody? Come on, who uses Febreze? Some of you use Febreze. Okay, William, why do you use Febreze?
The smell. I mean, I like the fragrance.
But what if I told you, William, that there were many ways to get good fragrances in your room? And what if I told you that Febreze, right, was, I think, and it goes on to talk about it in the article, Febreze was, okay, let me see if I can summarize this, right? It was their crown jewel product. They had predicted that it would sell like wildfire, but in the beginning it bombed. It bombed. And the reason it bombed is they had all these ads of, oh, let's take this really smelly room and let's clean it up and then use Febreze on it, right? And what happened is the brain, right, got negative impulses of, oh, I have to go clean this room, right? I have to do all this work and then I get the smell. Or no. Actually, they had it as, this is really smelly, let's spray it away with Febreze. And everybody kept thinking about that, oh, it's, this terrible smell. Like these things, someone talks about something smelly, all of a sudden things smell bad around you. You feel it, right? The neurons are firing. It's like mRNA, okay? It's not there, but it's there, right? And so what happened here is they changed the marketing tactics to make Febreze look like a reward, right? Like, you deserve a drink, right? So everybody goes and gets a drink. So now you deserve a Febreze. You see that? And just that, okay, turned Febreze into their top selling product from being the worst that they had, William. Right? So they use this, right? They use this data. Okay, so that's one. All right. All right. So, all right, let me see. There's another thing in here. Hold on. Yep, the guy got promoted. Right. This is the story on Target. The manager walks in, says, "What are you doing? Are you trying to encourage her to get pregnant?" Okay. And then he apologizes because Target figured it out, right? The argument is, did Target cause the pregnancy to begin with? Right? All right. And then Target should be apologizing. Okay. I still think it's up there. Okay. So, all right. And then, okay, yeah. So let me see. There's one more piece that I need to tell you. Here we go. All right. So they knew that they had everything. You guys need to look at this. This is like the most important piece of the paper. Second most important piece. Most important thing is they can control you, and they are controlling us, right? So you have to, now that you've come out of the matrix, you have to decide if you want to go back into the matrix, all right? Because life is good in the matrix, right? Ignorance is bliss, right? But you have to decide now, right? They talked about, so what they said is that with pregnancy progress, though, we learned that some women react badly. All right, the executive said. Then we started mixing in all these ads for things we knew pregnant women would never buy. So the baby ads looked random. Just think about that. You know what I mean? So, you know, they do that, right? And so we put an ad for a lawnmower, so they know what you are absolutely not interested, and they use that to disguise the programming. Right? So they know what you want, they know what you don't want, and they know how to set it up so that you don't see it coming. Right? And so, all right, and that way it looked like, or we put, you know, a coupon for wine glasses next to infant clothes, right? That way it looked like all products were chosen by chance. You see this? This is how they talk, right? This is how these decisions are made, right? And so, and then as long as we found out that as long as a pregnant woman thinks she hasn't been spied on, she'll use the coupons. She just assumes everyone else on her block got the same mailer for diapers and cribs. As long as we don't spook her, it works. Okay. So obviously there are ethical issues with all of this. I'm telling you that classification models can be done for good. They should be used for good, right? Big data should be used for good, but without a doubt, it has been weaponized, right? And advertising and stimulus control us, right? So I hope that you all enjoyed the lecture, right? If you ever need me, you can reach me at prem, prem@umd.edu. I'm happy to stick around and answer questions. But, you know, the world is very interesting, and data tells you what's going to happen, and data also controls what will happen, right? It's up to us to be able to put it together and hopefully do something good for it, do something good for the world with it. Okay, any questions? Yeah.
Any questions
Yeah.
for Trem?
Yeah, I have a question. This is Helena Thompson again. This is something totally different. You had mentioned something about the video game programmer.
Yeah.
Because I've been working on a game, but I'm using PyCharm and Pygame. Have you ever done video gaming or anything, or this is because you mentioned something about running games in parallel?
Yes. So I have done some simulation work that was related to video games. So we built like a video game that was a simulation for some math problems, right? And yes, so I have some experience with it, but yeah, you're asking. Go ahead. Yeah.
Okay. I guess the reason being is because I've done television production as well as some video animation, and I thought putting it together from that perspective, since I'm taking Python, but I do find that PyCharm and Pygame helps to get you where you're going when it comes to certain things like buttons and different effects and that kind of thing. But I just thought I'd do something that's fun with Python, even though this is fun as well because you're learning something that can help the public, mankind, and that kind of thing. But
you know, this is a very good point. What was your first name again?
Helena.
Helena. Okay. I didn't mean to cut you off. Go ahead and finish, then I'll elaborate on what you said.
Go ahead and elaborate. Go ahead.
Okay. So, oh yes, I'm sorry. So let me stop sharing. Okay. So, okay. So it's very interesting what you said, and I'll tell you, I had I had a student ask me 2 days ago, hey, I'm trying to get a job in the field. What are the things that I need to work on, right? And I said, look, technically you're sound, right? You have the skill sets, right? So the best thing you can do is have an example, a portfolio, a project that you worked on. But then I said, and this is where I think it's at, okay? And this relates back to your question. The ability to convey the story, right, to the critical users that you need to make a decision is more important than the model that you created. And I have found that there's a movie called Margin Call. Has anybody seen that movie? It's fascinating. Jeremy Irons is in it, okay? And he pulls everybody into a boardroom because the financial industry is getting ready to crack. The mortgage-backed securities they figured out are worth nothing, and everybody's foreclosing, okay? And he talks to this super tech, and he says, "Listen, stand up, breathe, be calm, and speak to me as if I was a 6-year-old or a Labrador." Right? And literally, right? And I'm like, did he like what? But that is what is necessary. You have to be able to tell the story. And if that means you have to build animations, if that means you have to build simulations and infographics, and you focus more time there, I cannot believe I'm saying this. If you have to focus more time there than you do on the math and the model, that is what you need to do. Right? And so I think what is going to happen is the visualization and the interactivity of the presentations of these models are going to decide which models get picked. I walk in there and say, we have 95% accuracy, plus or minus 1%, and we run in 10 minutes, okay? And you walk in there and say, here's the model actually running, and don't even quote any metrics, depending on who the user is, and let's say your presentation is beautiful, you are probably going to win. Now, what happens if you're both beautiful and efficient, right? Now you can reach the masses. So, I hope that there are games that come about that talk about math, talk about critical problem solving, right? We have games where you're blowing people up, right? We need games where people are escaping, like escape rooms where you have to put together patterns to get out of something, right? That's the kind of stuff that I hope is pushed so that we use this presentation power, because like advertising, that is what decisions are being made on. So like what you're doing, even if you're doing it just for fun, Helena, that's great, right? But you should realize that the power of persuasion that the visualizations and interactivity you have can go very, very far. Yeah.
Thank you.
Yeah, you're welcome. Thank you.
Yeah, because I was definitely trying to make decisions in terms of what environment, whether it's educational, whether it's health related, or just something personal, and the gender as well as the age. So I'm just looking at all of these different factors, how it can be, instrumental in helping people, even for the elderly, because they love games too, so.
And this may be the answer. I can tell you that if, let's say the US had spent more money advertising about the safety of COVID and distancing and masks, and we had games where people had to, stay alive by maintaining distance and going to get masks somehow, right? I can tell you we'd have been in a better position, right? So, yeah.
Any more
Thank
questions for? Okay, go ahead. Someone is talking. Go ahead.
Yeah. Your email address, is that in the chat or?
Yeah, let me put it here, yeah.
Okay.
Anytime you need me, anytime you guys have questions, my thought on all of this is we are connected, more connected than we've ever been, right? And some of us, we all have our trades, right? Like I need to learn more about psychology and I need to learn more about chemistry, but I have, my hands full trying to figure out what the bits and the bytes are doing. But if we come together and we work together, then we have a chance to beat these things, right? We have a chance to improve. We have a chance to get past these viruses and whatnot. So Yes, Edmund, yeah, hi, Edmund, I saw you. I got your emails. Yes. And so anytime I get a chance to talk about data science, it's very important because, one of my mentors, he said something to me, sticks with me. He says, you have to learn to listen. He had very specific advice for me. I don't know if this is just for me or not, but he gave it to me, right? He says, you have to learn to listen. I said, okay, I'm listening, right? Then he says, you have to pay the price. I was like, okay, fine. What he's telling me I don't want to do, but I'm going to have to do it. I understand that, right? I've heard that. And then he says, you have to pass it on, right? And that's why I do it, right? We're connected. And, I was fortunate to have someone give me guidance and help me learn some stuff. And I always feel better when I talk to people and help them learn this stuff because it's important. The projections are somewhere in the next 10 to 30 years. We don't know when, but sometime in the next 10 to 30 years, people will not have to work because AI will be doing it for you, right? Like the world is going to change, right? The world is going to change. MIT came out and said, if you make it to 2040, you can live forever because we will have basically eradicated disease, right? So, the world is changing and it's more and more data. And so I hope as many people get involved with it and benefit from it.
Yeah, so obviously, Prem is very passionate about data science, and we thank you very much for 2 days of another informative and excellent presentation, and then all your involvement from the beginning. And hopefully, if you have to do it again, I'm sure you will be around, and then you
Oh,
will
absolutely. Yeah.
the
It's been a privilege to meet all of you, and I'm so glad that these programs even exist, right? Like we have to protect technical endeavors and we have to work together. So if you're technical, please stay technical because we need more of that, right? And I'm glad that we're communicating. It's been a privilege for me. Thank you.
Yeah, thank you so much. And also for those of you still on the Zoom, the next module 7 is next week. It's not in 2 weeks. That will be next week, Thursday and Friday, same time, and that is what tools for applied data science using cloud-based platforms. So check your emails for the invite, and then we'll see you all next weekend. Everyone have a great weekend. Nana, you have something to say?
The survey.
Yes, again, make sure you complete the survey, and also check your Slack, because if we have any announcement or anything that we feel it may interest you, that is where we are going to post those information. William, do we have office hours tomorrow and Sunday? What? Ebel, yes. So Ebel has, well, I'm not going to talk to Ebel, talk for Ebel, but normally he has it Thursday and Friday, and I have it on Saturday and Sunday. And so far, I would say Ella and Azad, not to mention names, have been very consistent. We encourage others to also participate. We learn from these things. If you don't have time, that's fine, but it takes a lot of effort to plan this, and then we only have 2 or 1 person showing up. But that's what we have. And then a quick message for Prem. So Prem, we still have we'll still be having that chat, the Slack. So we will say as a resource would kindly ask that you don't cut yourself out. And then when you encounter something, just drop us some bones on Slack.
Sure.
So we can also keep updating
Absolutely.
our skills.
Oh, and let me leave you guys with one more thing. So research has shown that it has very little to do with the talent you have and much more with the network that you have, how successful you become. So all of you reach out to each other, find me, I'm on LinkedIn, or send emails, but stick together and build your network, right? The more we are together, the more we know.
So I'm going to reach out to you about Bitcoin and crypto.
Yeah. It's a play against the US dollar. As long as, John, listen, John, we cannot just keep printing money, right? And did you guys see that China's GDP was up 18.3%?
Yeah, it was, yeah.
I don't even think the US has a GDP right now, right? And so, like, GDP growth is negative, right? So they're up 18%. We cannot just keep printing. And that's why Bitcoin continues to run. People are scared to put money in US dollars.
But it's okay. So have you not too late? So those of you who are not involved, we can still participate in cryptos. Is it not too late for us?
I think, my spin on, I'm not a financial advisor, but here's my spin on this, right? If you have the $1 billion problem, okay, so this doesn't happen to commoners like us, okay? So let's say that you're a hedge fund or you're a trust and you have billions of dollars that you have to park somewhere, right? Well, do you put it in these savings accounts and make nothing, right? Do you park it in equities? Maybe, but you can't afford that much risk, right? Because you're handling people's pensions. So what they've done is they've said, okay, we believe that Bitcoin is a hedge against the currency, so they park the money in Bitcoins as opposed to keeping it in cash. Now, you and I don't have that problem, John, right? So I think you're much better off, in my opinion. I like star US companies, right? You always have to have some cash, but I would not buy Bitcoin or anything at this point, right? And that's because all bubbles pop. Anytime someone is running, everybody's running in one direction, I am the guy running in the other direction.
On the other way.
That's how and so bulls make money, bears make money, pigs get slaughtered.
Okay.
Right?
Okay.
Listen, the only stock I like is Tesla. That's the only stock in the universe that I like. That's why you saw the Tesla stock there. And even now, if any investment you make has to be for 10 years out and never play with margin. Those are my financial rules.
Yeah, I hear there is a coin coming up named after Elon Musk, Elon Gate. You heard about that?
I saw the infographic as well, John. Yes. So he's a funny guy, right? So yeah, I don't know. Yeah. stick with cash and long-term investments. I would stay away from crypto at this point. Unless you have $1 billion, you got to park, right? If you have $1 billion, you got to park. Then you could do it. Yeah.
Okay. All right. It has been very welcoming, very interesting, and very informative having you. So
thank you so much.
We'll get in touch, Prem.
Yeah. Thanks so much. Talk to you all soon.
All right.
Bye.
Okay. Bye, everyone. Thanks. Something to go out.